Okay, so welcome everyone. I'm very happy that a lot of you could join live. This is the first of the series about the data webinar. This is the first webinar of the series that will be dedicated to Data Lakehouse, but Marek will say more in a few minutes. So yeah, to not further ado, I will give the voice to Marek, who is our Chief Data Architect and the best person to present any data architecture or any data solution, I think. So yeah, I'm also very interested in what we're gonna hear. So Marek, the voice is yours.
Okay. Uh, thank you again for the introduction. Thank you for joining me today. As Silvia mentioned, today we are starting a series. We even call it a season one. We are starting a series of episode dedicated to data lakehouse architecture, and what you can expect from this series. So this series will be about 5 to 7 episodes that will during which we are going to go deep into very interesting aspects of implementing, building, and also working within the data lakehouse environment. So basically speaking, over the next few episodes, we are going to go deep into the technological landscape of both proprietary and open source solutions, technologies that you can use for building your own or like implementing from the existing platforms your own data environment. We are also going to touch base on the business impact, how to organize the projects in a cost-efficient way, how to also implement the data lakehouse into cost-efficient way. We are also going to share our experience from the past projects, how to organize the projects, how to how to conduct the project in a way that it turns out to be a successful implementation. We will dedicate a lot of time discussing the cost aspect because we are aware that costs nowadays are one of the crucial aspects of the data platforms, as data platforms seems to be large-scale projects that, if done not correctly, if implemented not correctly, can cost you a fortune. And without providing you with the expected results, with the expected boost to your organization, can cost something quite to the opposite. I'm also will focus a lot about the emerging trends and what's happening on the market, because right now we are experiencing a very interesting point of time when there is a kind of paradigm shift from the let's call it like a first edition, first version of data lakehouse architecture, and we are gradually, as the title of this series suggests, going towards so-called open or even composable open data lakehouse architectures. Especially today, I would like to introduce you the some of the basic concept, what is actually all about data lakehouse, what are the core building blocks, what is special about this architecture, how it differs from the previous generation of data warehousing and data lake. In the next few slides, in the next few episodes, as I mentioned, we are going to zoom in into a specific aspect when we focus more not only about on the theory, on the concept, but also about some practical examples, some ready to implement design patterns, some critical aspects to pay attention to. And we also, from time to time, would like to show you our own benchmark, proving that adopting one technology or one approach over another can bring some additional benefits. Let's start. I will start with some brief introduction to the history of data lakehouse. So if you are new to the business, you may only associate or predominantly associate data lakehouse architecture with one of the biggest advocates of this technology, namely Databricks. But the reality and the history is more nuanced. So this concept is dated back to 2017, if I'm not mistaken. It was the first time on one of the meetup, Jerry and Ingalls coined the term data lakehouse. But something that you need to be aware of, that initially data lakehouse wasn't that well formally defined. It was rather a kind of idea, something nice to have, that some like a very imaginary scenario, imaginary architecture without involving too much details. An architecture or platform that can efficiently handle both, so structured and unstructured data. This is why the focus one was on the schema on write and schema on read. So these are two approaches for working, two strategies when working with structured and unstructured data. So initially it wasn't very sophisticated. It was like something that people always wanted to have since the introduction of Data Lake, because if you turn back the time, with everything, the analytics at large scale started with data warehousing, which then evolved into Data Lake. That's supposed to be like a superset of feature of data warehouse, but it failed to do so. Yet there is a hand raised. We have a question. This is why ever since people wanted to make or get the best features from both, from data lake and data warehouse, to have a single platform to rule them out. Yeah, that was 2017, but in 2020, Databricks started to more formally, define the ideas, the concept, the like we say, the main points that the Lakehouse platform should address. And it was until their very well-known paper that was published in 2021, entitled Lakehouse, a new generation of open platforms that unify data warehousing and advanced analytics. And in this paper, people from University Berkeley, University of California in Berkeley, and also that was also a part of the Databricks company, emphasized a few very important aspects about data lakehouse architecture. So first and the most important ones were you got on this slide. So first of all, there's supposed to be a unified storage system for structured and unstructured data. So in order to efficiently process both of them, you need to have a storage system. Let's leave it for now like in a very, very generic term, like a unified storage system that can handle efficiently both, because that's the idea from the data warehousing and data lake that is unified within one platform. Next goes something that was originally from the old relational database management system, like transaction support, data versioning, that also supposed to be present on the platform. And the idea for that was that we should somehow enhance the existing data lake storage system that mainly focus on the file abstraction. And you should introduce a table on top of that to provide something similar to the old data warehousing systems. Finally, we should expect from the platform SQL performance that would be somehow on par with data warehousing, which wasn't the case of data lake platform, when of course we got some technologies, some system that allows end users to use SQL abstraction, but the performance, if you remember times of old Hive systems, data warehousing system, you remember that the performance was far from being perfect. Next goes something that was very well implemented, available on Data Lake. That was the support for machine learning. But the thing was that we couldn't use the same approach adapted from Data Lake to Data Lakehouse in order to get machine learning support. This is why there's something that we need to figure out how to do efficiently. Next goes metadata, because that was something that was clearly not sufficient in the Data Lake platforms. Of course, you are able to have some basic metadata that you were able to have a table abstraction to some sense, but you are, for example, it wasn't that easy to, for example, achieve transaction, time travel, queries, and stuff like this. So it had to be redefined, and it was redefined in the Lakehouse ecosystem. And finally, something that were neither from the data warehouse or Data Lake platforms was decoupling of storage and compute. That's something that came with cloud environments, when by design it was possible to scale out the storage and compute separately to have something like unlimited scalability options. So the bottom line and the basic idea was to replace the second generation of platforms when we have like a separation of warehousing and data lake features, and introduction and something that unifies both type of workloads. And the promise was that this platform should be open, but as we show along the way, it wasn't always the case. So if we take a closer look at the Data Lakehouse architecture, and if we were to simply explain what is or what are the building blocks that constitute the Data Lakehouse architecture, we can easily point out three layers: the storage layer, the compute layer, and metadata layer. So the storage layer is a kind of evolution of something that we got in Data Lake, because we use, for example, the same open file formats for laying out the data. But we have like an ingredient from the cloud. So we got like in most of the cases, we have cloud storage, relying on object storage cheap and scalable storage provided by cloud vendors. Of course, it's always possible to use the open implementation of the cloud storage and have it on premise, but let's now like focus on the cloud deployments. And on top of that, we have this open table format layer. This is the transaction and data versioning layer on top of open file formats like Parquet, ORC, or Avro. That gives us additional layer of that enables us to have something similar to relational database systems. So we are able to version our data. We are able to have isolation between transactions. So we are so-called ACID compliant. Next goes the compute layer. This is something that initially was taken as it was from the Data Lake. So in most of the cases, there were the same query engines like Spark, Apache Flink, Trin, or previously PrestoDB, PrestoSQL. But we will later on show that these compute engines also have evolved and have been adjusted to the Lakehouse environment. And there was yet another layer that was really evolved in the Lakehouse architecture, was the metadata layer. Of course, in Data Lake and data warehousing, we also have something similar. But in order to fulfill the requirements that were from both worlds, from data warehousing and Data Lake, in the cloud runtime, we needed to redefine this metadata layer that evolved in so-called data catalog. So we have like storage layer that constitutes of three subcomponents. We have processing engine and data catalog, and these three pieces all together constitute the Lakehouse platform. I said you in the beginning that the idea behind Lakehouse was from the very beginning was that it's supposed to be an open and cost-efficient platform. But the reality was that the main advocates of Lakehouse architecture, so Databricks and Snowflake, actually developed platforms that were quite close. Of course, you may say, hey, wait a minute. For example, Databricks relied on Data Lake format that was open source project. Also, Apache Spark was an open source project. Also, MLflow. All these were open source. And also, on the other hand, Snowflake enables you to use open file formats like Parquet or ORC as an input data format. Also, along the way, have introduced support for Iceberg as one of the table catalog that was table formats that was possible to exchange data with the outer world. But the thing was that this integration with third-party tooling and data exchange in a secure and controlled way was not that easy to implement. It was until mid 2024, so like around June 2024, when both vendors have their own conference, and within 2 weeks, within a 2 weeks period of time, they open source their data catalogs. So on one hand, Databricks open source Unity catalog, and also Snowflake almost at the same time introduced Polis catalog as an alternative, and both claim that they are the open source catalogs of choice for implementing really open Lakehouse architectures. And that was actually a game changer because these two events triggered appearance or emergence of a number of other data catalogs, and also made it possible to integrate third-party tooling to re-implement your data lakehouse in a more open fashion, meaning that you no longer need to use only the manage compute, manage storage, and manage metadata layer from one of the vendor, but you can implement a kind of bespoke or customized version of Lakehouse architecture, where when you are to decide which components, which compute engines, query engines to use, and how to efficiently exchange data. Once maybe maybe let's clarify that why it was really a game changer. Because if you take a look at the diagram on the left, you can see that it was always possible to bypass the data catalog layer and access the data stored, because no data were stored in open format. They are stored on object storage that all of them, no matter which cloud you use, have well-defined APIs. So there was always an option to access the data somehow, period. But the thing was that if you were bypassing this data catalog or metadata layer, and you are directly, for example, accessing the file torrent, you are losing a lot, because you are sacrificing the whole data governance just because you would like to read or write the data. Data governance means that you are bypassing the features like data discoverability, access control, data lineage, audit features. So without open data catalog, it wasn't easy to seize the opportunity to have all these features within your Lakehouse platform, and at the same time using, for example, open source query compute engines, at the same time using different file formats. And this movement caused that it was finally possible to implement something that we called composable open data lakehouse architecture. And you may wonder what in this aspect really means composable and open. So maybe let's analyze this diagram a bit. So we again have this on the left-hand side, we have these three storage layer. So starting from the bottom, we have storage layer, metadata, and compute. As you can see, if we decompose the storage layer even deeper, we have the option to always to choose what storage object storage to use. And we can even always turn to open source solutions that implement, for example, S3 APR or protocols. We can even use well-known HDFS storage. It's up to us how we're gonna store the data. Next has the sub-layer of open file formats, and again we have an option to choose any of this. And finally, we got these table formats. And again, we are no longer need to stick to Iceberg or Data Lake and Hoodie, because behind the scenes, all these table formats rely on the well-known file formats. They only, that may be oversimplification, but the main difference between them are the metadata layer. So straight away, there pop-ups projects that helps to unify this metadata layer. Unify here means like asynchronously generating metadata for more than one open table formats. For example, you can store the data that are in the tables registered in Iceberg, and at the same time using technologies like Xtable or Data Uniform makes it possible to read the data by clients that, for example, expect data lake metadata format. So right now it's fully open. So the storage layer is fully open. No matter which table format you adopt, you are no longer in a position when you need to somehow adjust your clients, because it's always possible to write the metadata in multiple formats, so that no matter what client you use, you can always read and write the data efficiently. Next, we got this metadata layer, and here again, we started with some closed data catalogs a few years ago, and right now we have great selection of both business and technical. Business catalogs are the catalogs that are mostly about the business metadata, like some glossaries, some tags that somehow helps end users to navigate and look for the right data sets to use. Whereas technical are the ones that are needed for stuff like access control, like data lineage, observability. So again, we can pick up either the commercial one that are available, for example, and hosted by Databricks, Snowflake, or other vendors, like for example, Amazon. But we are also free to use open source alternative. And what is even more important, even if we use, for example, commercial one from Databricks, I would like to emphasize we are able to access the data in a secure fashion from open source clients, and we are no longer somehow in a vendor lock situation. Next goes the compute layer. This is something that I already mentioned. So we have at our disposal both commercial processing engine and open source. And in the next few slides, I would like to also tell you about some new trends, something that we right now observing, how these query engines, especially when the open source, are evolving, because the fact is that we are no longer only relying on distributed engines that can work in the Lakehouse ecosystem. We have single nodes and also some hybrid solution that combine or well-known projects like Apache Spark with some additional acceleration layer. Yes, and let's maybe discuss first these native backend options that we have for the compute. That was something that was introduced by Databricks already 2 or 3 years ago. The idea here is quite simple. So as you know, Databricks relied on Apache Sparks and as their main query engine, processing engine, both from batch and stream processing. But the problem, or maybe the challenge with all these big data tools like Apache Spark, Apache Flink, well, generally speaking, almost the whole big data ecosystem is that all these tools were implemented using JVM languages. JVM meaning that they are implemented in language such as Scala, Java, that are executed within the Java virtual machine. The good thing about implementing something in Java is that you have for free memory management, that there is a rich ecosystem of libraries. So now, so to sum it up, it's fairly, maybe not easy, but it's quite convenient to implement large scale, complicated, complex projects using JVM ecosystem. But the problem is that in many cases, the usage of automatic memory management with automatic garbage collection and using this virtual runtime like JVM have some negative impact on the performance. And it can be twofold. First of all, using JVM for automatic memory management, in most of the situation causes that the software uses more memory than it really should, because there is some overhead of garbage collection of the runtime. Garbage collection cannot happen in the real time. There must be some over allocation of memory because the JVM needs to be prepared of some growing heap size. And this is why in most of the cases, JVM systems, so running on virtual machines, have very huge memory requirements. And it also comes with some overhead of the fact that the code that is run within JVM is not natively compiled, meaning native compilation, meaning that you are able to compile your source code into the machine code that is specific for your processor. So it's not trivial to take advantage of some, for example, SIM extensions, so vector processing, some low-level cache tricks if you are running in the virtualized environment. On the other hand, using languages such as C++ or recently Rust makes it possible to compile your code into the executables on machine code that is targeted for your hardware. So it really can be optimized for your current infrastructure. And combining these two things, so like a performance of compiled languages, as well as like memory safety, and also a lot easier programming within JVM world, resulted in projects and resulted in a system like, for example, Photon that was initially introduced by Databricks. When you preserve for example, in the case of Photon, the Spark engine as a front end to the users and applications. So you preserve the API, also the part responsible for task generation, for query optimization. But later on, once the query is once the physical plan is fully generated out of your queries, it's sent back to the native engine. And in case of Databricks, it's called Photon, which is written in C++. And it claims to provide similar like a 2-3 times performance boost. And we observed that there are some open source alternatives to the idea. For example, the project called Apache Data Fusion Comet or Apache Gluten that follow the same idea. So if you take a look at the right-hand side, you have a diagram when you have some Spark job decomposed, and you see the Spark operators that are marked in yellow. This one can be executed either within JVM or can be sent to the native backend in order to get some performance boost. So to sum it up, we observe right now the movement where all these systems like Spark, Flink, get some steroids, so they are able to process your queries faster. And it's also, it applies both to this proprietary commercial engines as well open source. By the way, the project Velox was open sourced by Meta, because also Meta is following the same idea. And for example, project Apache Data Fusion Comet is supported by Apple. So like a large companies are also investing in that one, because by seizing the opportunity of using native backends, you can really cut cost of your infrastructure if you are running your queries and scale. So you can like minimize the memory footprint as well, like really speed up the queries by a factor of 2 or 3 even. Next movement that we observe is that in many cases that was always something that we also observe as a consulting company, that many of our customers really wanted adopt or enter the big data world, but in fact the scale of their data and also the complexity of their queries and data processing didn't require such an overhead. And because of that, we also observe emergence of system solutions like, for example, DuckDB, Polars, or Daft, which are a single node systems by design, but they offer out-of-core processing. Out-of-core processing meaning that they are able to adopt a streaming fashion of processing, and they are able to process data that have a size larger than the main memory of the computer by using streaming or queuing systems, but with, of course, implemented in a very, very performant way. So they are like a parallel streaming-oriented processing engines that in many cases can like handle very large or mid to large scale workloads. Maybe not like not on all kinds of workloads, but in many cases when we combine these engines with like a large single node instances, we are able to cater for 90% of the workloads that many customers experience. And again, by doing so, we are no longer needing to run computation on a distributed cluster if your workloads or data size are rather for a single node size processing. But one more thing that comes with that solution is that they also offer kind of hybrid query processing. And hybrid processing means here that you are able to process data both locally and also in a distributed fashion. So something that was kind of that was available also in, for example, Spark, when you could run your queries locally, and then you only were able to utilize the cores within your local machine, but you were also able to run your queries in a distributed fashion, for example, of Hadoop cluster. But they move it even further because you are able to combine them within one, for example, queries. For example, some of the processing can be run locally, when, for example, some small size processing on smaller data set. And if you, for example, also join some large data set that it cannot be easily handled in your machine, and it's stored in the cloud, it can be computed or processed there. So you can like have the benefits of both. The thing is that these tools are pretty new still and not fully integrated with the Lakehouse catalogs, but this is something that it should be definitely observed, and you should observe. Our colleagues from Netherlands even gave a great talk about like a Duck Lake approach when we, as the name suggests, combine DuckDB with the Lakehouse architecture. Next thing that I also observe, the movement I observe, and also I'm personally involved, is the rise of highly optimized and specialized engines. And again, it's thanks to the fact that we have this data, open data catalogs, and we are able to use some third-party or even custom tooling if needed. So here we got the idea that we can even build our query engines from the scratch. Right now there are available projects that gives you some building blocks like query optimizers, like execution engines that are highly extensible, together with some well-known interfaces like DataFrame or SQL. And by adapting a project like, for example, Apache Data Fusion, you can easily create your own domain-specific query engine with some optimized operators that you can have, again, massively cost optimization, because first of all, it's written in natively compiled engine, so you don't here have any data exchange between JVM and your native backend. Everything is running within your native backend. Only the final results can be passed to some user-friendly interface like Python data frame. But again, by using tools like Data Fusion and Apache Arrow for this zero-copy data exchange, you are also able to fairly easy implement your highly optimized engines and plug into the data lakes ecosystem. I personally developed one that is called Polar's Bio, that is meant for large-scale processing of genomic data. It turned out to be it turned out to give enormous performance boost when compared to existing Python libraries, because again, it runs behind the scenes using a natively compiled language and on high performance data fusion execution engine. Finally, we also see that streaming is becoming the first-class citizen of Lakehouse architectures. We even saw a concept of Streamhouse, something that was just recently introduced. But the idea is again very simple: that we use existing and very well adapted to streaming processing engines, like for example Apache Flink. But we adjust the storage layer. So here, for example, we have a dedicated file format called Apache Pymon, which you can use for that purpose. So the purpose of high-speed data ingestion, CDC workloads, and also you can efficiently query it in a batch and streaming fashion to have real-time analytics-like systems. And what is even important, since we again have these open data catalogs, there are already existing integration with these open data catalogs, so that you can register the tables backed by this file format and query them from some other analytic system, like for example StarRox. By the way, StarRox is one of the solutions that you should definitely observe and track, because they are becoming a star in the area of near real-time analytics. Also, if you take a look at the data catalogs, you will see that they are not only meant for structured data, but they are also meant for data, for volumes, for registering machine learning models. And finally, just recently, they are also entering the LLM and AI world, generative AI. Because some of the catalogs recently, like for example, Unity catalog, added support for function calling. Function calling is the ability of a large language model to call some external tools, like for example, Python code or some other tools. And for example, you can still register these tools within existing data catalogs, manage the access rights to these data catalogs. To these functions, and by doing so, your AI agents can have access to already registered functions. And there are already existing integrations with popular frameworks like LangGraph, LangChain, or LightLLM that you can fairly easy access the registered functions and data that are registered within the open data catalog. So you can easily adopt LLM and ML ops principles using data catalog. Of course, it's not the only it's only piece of the only solution that are required for implementing ML on LLM ops platforms end to end, because you still would like to have some observability and experiment tracking components. But still, for discoverability and governance and inventory of existing models or functions, it is already available. So you can easily extend your lakehouse with some ML and Gen AI features. So if I were to show you just one slide and something that I would like you to memorize as a take-home message from today's presentation, is that the Open Data Lakehouse, you can visualize it on a kind of continuum. When on the one edge of this continuum, you have like a fully bespoke data lakehouse platform. Fully bespoke means that you rely only on open source components for compute, catalog, and storage layer. And on the other end, on the other edge of the continuum, you've got like a fully managed data lakehouse. So you rely mostly on the managed compute, managed catalog, while still preserving open table format and cloud storage. And you can imagine that nowadays it's possible that you implement your own data lakehouse that can be somehow between these two ends. So these are depicted as this blue shape here on this diagram. So it can be maybe less complex, but at the same time less flexible when implemented only with using managed components. But it can be somehow closer towards the end where it's possible to have it fully flexible and at the cost of greater complexity, or it can be somehow in between. So it's up to you. It's up to your needs, up to your business needs, up to your technical requirements when you place your lakehouse nowadays. So what are the concluding? So what are the business benefits of implementing a platform that is following this open data lakehouse principle? So as I already showed you, you got a tailored platform, so something that is truly adjusted to your needs. You don't need to sacrifice any functionalities because right now it's up to you how to implement your, for example, compute layer. You have also freedom of selection of the tools that you would like to use for query processing. You can, for example, have within one platform single node tools that are meant for like a simple or like not that computationally intensive task, but you can also option of running fully distributed, well-known engines like Apache Spark, Flink. That's up to you. You are no longer forced to use, for example, distributed clusters when the size or the complexity is low, and you can optimize your spendings by using cheaper alternatives. And this cost optimization is something that we would like to very, very much emphasize here, because by this flexibility and openness, we can help you to design and implement your lakehouse that is truly optimized to your needs without over-engineering, without relying on the components that are, for example, too complex for you, or the computation resources that comes with this components are actually does not fit your needs because they are oversized simply. So you can truly adapt your computation, which is in many cases the main factor, cost factor. You can truly adjust it to your need. When we take a look at the technical benefits, is that because we right now are in the position when most of the lakehouse components have their open implementation and well-defined open standards behind them. The integration right now is rather seamless, so you can always try to adjust your components or selection of the components to your need, and you shouldn't expect any integration issues because most of the components are right now following the open standards. The current architecture of the data lakehouse is no longer monolith, so you are free to mix the components from the open source and build with the commercial ones. Of course, there are still, in some cases, there are still some things that are not fully implemented, but it's just a matter of time that they will be, and it should be possible that most of the components can be used interactively. Scalability, here you don't need to over provision resources or use too complex tools if you are running something rather of small workloads or not that complex one. Since most of the components right now of the Lakehouse comes with existing providers, for example, for Terraform, it's possible to provision your platform using this infrastructure as a code principles. And what is even more important that right now it's possible to avoid any vendor lock-in when implementing Data Lakehouse VR, because it's right now becoming truly open platform. And one more thing that that I would like to you to and I would like to leave it as a take-home message is that we are strong advocates of DevOps principles, and since right now everything is relying on the open standards, and it can be fairly easy automated with infrastructure as a tools, we are strongly advising to not start implementing anything without adopting the CI/CD and infrastructure as a code principles. And I just wanted to highlight that because I heard many times that it's something as an additional cost. And here today I'm talking and emphasizing this cost effectiveness of data lakehouse implementation. And this is something that also should contribute to this reduction in cost. So if someone is saying that no, this will introduce some additional cost or slow down the project, please don't believe, because all the consulting companies that are truly into Lakehouse architecture have their own accelerators built in that can help you to bootstrap your Lakehouse platforms, so you can actually accelerate your project, not block it. And the final question is whether this open Lakehouse or data Lakehouse architecture is always a good choice. Because I showed you in the slides that there are some research showing that most organizations don't have big data, that most of the workloads are smaller than the data sizes, and right now it's possible to run even large scale workload using a single node. So you may ask your question if data lakehouse is something that you should consider as a good option for your data platform. And here I would answer as an consultant. So it depends, but let's quickly go through some edge case or corner case that may give you some idea whether when it's good to follow that architecture or implement platform following that architecture, not really. So if you got really tiny data, I call it like a laptop scale or notebook scale, and the workload is rather a simple BI, and you have only a few business users, then maybe Lakehouse architecture is not something that you should adopt because there are maybe better options of sticking to old data warehousing. Because you won't benefit from that much, at least not in the beginning. If you got some laptop scale plus workloads, so a bit larger, maybe some mixed workloads, not only BI, maybe you got some machine learning, or you are playing with generative AI, then there's something that you should already consider as an option. And finally, if you got, of course, larger scale, you got like power users that are also doing not only BI or reporting or running reporting, but also doing some serious stuff around machine learning or maybe generative AI. This is something that you should seriously consider as an option. And the question was whether open data lakehouse is a holy grail that we've been looking for. And my answer would be as follows. So this concept really evolved over the last few years. Initially, it was just the idea of processing the structures and unstructured data both in a single platform in an efficient way in the cloud. But right now, it's really a well-established and robust idea. Since the open sourcing and this openness movement that was initiated 1 year ago, it's becoming de facto go-to platform for a platform that is open and flexible and can address all the business analytics needs in a really scalable and cost-effective way. So my answer would be that in most of the cases is something that we were really looking for. Thank you for your time, and now it's time for questions if you got any.
We have some question and one comment about JVM-based projects. I saw some Spark-like implementation in Rust in a GitHub in the past. That is from Mario Amatucci comment.
Yeah, so this is, for example, this Apache Data Fusion comment is a Rust accelerator for Apache Spark, and that is written in Rust. And also Gluten project, Apache Gluten, follows the similar idea. It's not written in, it's also relying on Rust and Data Fusion. Yeah, so these are the two most promising open source alternatives to Python. Yes.
One quick question from Przemek. Iceberg or Delta?
Iceberg.
Really
that
quick.
Was a quick one, so the answer was quick.
Yeah, and Marcin asks if was Bill Inman also involved in creating it?
Yeah, so because it's a data warehouse related, I'm not sure, but I think I saw his idea for layering or modeling the data for Data Lakehouse. But I'm not an expert in data modeling, but we can double check that. But I think he was involved in that.
Okay. Two more questions. Apart Databricks, who is doing proper lakehouse in your opinion, Marek?
Xebia / Xebia. No, it's a difficult question because I think that as long as a company or vendor is sticking to open formats and adopting the principles that we presented today, I think it's worth considering. But it strongly depends because I'm truly on the open side of this movement. So as long as companies are open, meaning using open source friendly project, then I think yeah, they are good to go. This to consider.
Are any of the open catalogs actually suitable for production?
That's a very good question. Right now, my suggestion would be to stick with the commercial ones, as the open source, at least are not, in my opinion, production ready. But I think it's a matter of months that they will become because they are progressing very quickly. But right now, I wouldn't recommend to use these data catalogs for production workloads. But I think it's a matter of time.
The comment from Marcin. It seems that data lake can be discussed from two perspectives. One being how we model data, medallion architecture, and second, focusing on technical architecture, which is like in Marek's presentation.
Correct. I think we will have a dedicated session on medallion architecture and on organizing the data in the Lakehouse platform. So then we can go into details. Today, I want to just like highlight some aspects of that, not going too much into the details, but for sure we will address that.
Yeah, remember that is a series. Like
exactly.
It will be better than in Netflix. So yeah, wait for it. Serverless compute, yes or no?
Depends, but in many cases, I would say that it's really worth considering. Maybe not like large scale ones, but for example, for like SQL workloads, it's something that no, there are of course aspects of data security and where the compute resides, but yeah, something to still to consider.
Yeah, and the last one, any predictions when Apache Pymon will be supported by cloud providers?
Hard to say. It's still relatively a new thing, so I don't know. But this is something that we are really observing. So I would again expect that this format it might be something that will become like a core building block of streaming capable lakehouse architectures.
So a comment from Marcin Spot, very solid first episode of the series. Thanks, Marek, for the content.
You're welcome, and stay tuned for more.
Yeah, so I will share with you all the webinar recording as soon as I will process it. Also, we will ask you for feedback about this episode, and maybe we will share some survey. What do you want for the other episodes of the series? Of course, we will also invite you to the next episodes. If you have any ideas on how to develop this topic, what questions we should address, just write us on email. When you will get the email from us, just write back to us, and we will try to cover this topic as good as we can. So yeah, thanks Marek for a great presentation, and thank you all for attending, and see you soon. Also hope even with more attendees in next time. So thank you.
Thank you.